So welcome viewers. Today we will discuss what is known as Ampere Circular Law. Okay, what is Ampere Circular Law? It says that the line integral of the magnetic field B bar around a closed loop, around any closed loop, that is circular integral of B bar dot dl is equal to mu naught times the net current I enclosed by the path. Okay, this is the mathematical definition of Ampere Circular Law. Okay, circular integral of B bar dot dl bar is equal to mu naught times the net current I enclosed by any path. Okay, right now this is Ampere Circular Law. Okay, one important aspect in magnetostatics. In electrostatics, we have Coulomb's law. Okay, using Coulomb's law of force, we can find out electric field due to any charge distribution. Okay, but when the charge distribution is symmetric, like charge is in a wire, okay, linear charge distribution or spherical charge distribution or aerial charge distribution, whenever there is some symmetry in charge distribution, we use what is known as Gauss law. Okay, Gauss law is the fastest method to find out the electric field vector at any point, okay, because of symmetric charge distributions. Remember, Gauss law is applicable are useful only when the charge distribution is symmetric. That's what we will be seeing in electrostatics. Similarly, in magnetostatics we have Biot-Savart law. Okay, with the help of which we can find out the magnetic field due to any current, any wire carrying any amount of current. But if the current is symmetric, okay, if there are some symmetry aspects, okay, due to the for that current flow, okay, it becomes very easy to find the magnetic field using this Ampere Circular Law. Okay, right, all the thing we have to do in Ampere Circular Law is we have to evaluate this circular integral of B bar dot dl bar. What is the meaning of evaluation of this integral? Okay, right now this is nothing but circular integral B dl cos theta. What is theta? Angle between B and dl. Okay, if the angle between B and dl, that is theta, is well known or is uniform or varying in a systematic manner, constant. Okay, right, cos theta is known, right? If I choose a path where the magnetic field is constant throughout that path, B is constant, B can be taken out. Integral, circular integral dl, if it is a known geometrical figure whose perimeter or what's called circumference can be easily found, okay, circular integral dl also will be known, then I can easily evaluate the circular integral B dot dl, that simply make it equal to mu naught times the net current I enclosed by the path. Means what is important, just like in Gauss law in electrostatics, you have to choose a proper Gaussian surface to evaluate that surface integral in Gauss law. Here you have to choose a proper Amperean path to evaluate this line integral. That path should be taken in such a way such that angle between B and dl is known to us. Okay, B if it is constant throughout that path, well and good, or it should be a known value. Okay, and integral dl should be known. Okay, right, when you choose an Amperean path in such a way, it becomes very easy to evaluate this integral. Once this integral is evaluated, simply equate it to mu naught times the net current I, you will find out B value. Okay, this means not that we cannot use Biot-Savart law. Okay, Ampere's law gives you the magnetic field in the fastest way. Okay, one example, one application of Ampere's law is like this. Okay, B due to an infinite long thin straight wire. Okay, this we have already seen in Biot-Savart law. We have derived this also. Okay, B due to infinitely long, thin, straight current carrying wire at a perpendicular distance is mu naught I by 2 pi r, we have seen. Okay, and if you remember, this derivation is about one-page derivation in the textbook also. Okay, it comes for 10 or 15 marks in the university examinations. Okay, obtain the expression for the B due to a thin, long, infinitely straight wire at perpendicular distance r from it. Okay, using Ampere Circular Law, it becomes very easy. We'll get the answer in just 2 or 3 steps only. Okay, how? We'll see now. This is a thin, long, straight wire carrying some current I. Now for clarity purpose, the magnetic field due to this wire will be like this concentric circles. Okay, in this direction like this. Okay, right, what is the magnetic field at any perpendicular distance r? B equal to mu naught I by 2 pi r we see. Okay, how to get this result using Ampere Circular Law is the fastest way. Okay, right, now I'll change the figure. I'll tilt this entire figure so I'll see that current is pointing into the board. Okay, means wire is like this, current is pointing into the board. Due to this, magnetic field lines will be, right, concentric circles like this, concentric circles like this. At a distance r from the wire, B lines are what you call circular like this. Okay, right now what is the magnetic field at any point on the circle I want? Okay, now for this what do? I'll consider a small element of length dl, but its direction is also assumed to be in the direction of the magnetic field only. B at this point is in this direction, means tangentially downwards like this. dl also I'll take to be in the same direction, that is dl bar is also in the same direction like this. Similarly, I'll consider a small element of length dl here. Okay, the length of the direction of dl is assumed to be in the direction of the magnetic field, means B bar also is tangential, dl bar is also in the same direction. The angle between B and dl bar is 0. Everywhere dl bar and bl bar, right, their angle, they are in the same direction such that angle between them is equal to 0 like this. Okay, now I'll apply Ampere circuital law, circular integral B bar dot dl bar. Okay, B bar dot dl bar here. Okay, circular integral B bar dot dl bar equal to, okay, if you expand this, it is circular integral B dl cos theta. Angle between B and dl, theta is equal to 0 degrees everywhere on the circular path. This circular path is known as Amperian path. Okay, right, so theta is equal to 0 degrees, cos 0 is 1, so circular integral B dl cos theta is nothing but simply circular integral B dl, circular integral B dl. Okay, now throughout this path, right, B is constant. Why? Every point on the path is at a distance r from the wire, isn't it? So B is same, right, here, 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 everywhere, means B is constant throughout this Amperian path. So I can safely take B out of the integral and write this as B into circular integral dl. B into circular integral dl. Okay, right, now what is circular integral dl? dl is a small element in this path. Circular integral dl means the length of this entire circular path. Length of this entire circular path is nothing but 2 pi r, circumference of this circle. So circular integral dl is nothing but 2 pi r. So this is nothing but B into 2 pi r. This is circular integral B bar dot dl bar. Means, see, within 2 steps I could evaluate circular integral B dot dl. Because how? Because angle between B and dl cos theta is known to me, 0 degrees. Okay, B is constant everywhere. Okay, right, means the advantage of choosing the right Amperian path is cos theta become B cos theta same everywhere. So I could, within 2 steps I could evaluate circular integral B dot dl. Now the next step is what? Simply, right, equate it to mu naught times the net current I, that is B into 2 pi r equal to Ampere circuital law says, right, mu naught times the net current I. What is the net current I enclosed by this path? I only. Net current is nothing but enclosed by this path is nothing but I only. So simply B equal to, so B into 2 pi r equal to mu naught I, or B due to this wire equal to mu naught I by 2 pi r. Mu naught I by 2 pi r. Okay, right, means what has taken what you call 1 page derivation in using Biot-Savart law, we could derive that, right, using Ampere circuital law within 2 steps or 3 steps like this. That is the advantage of using Ampere's law. But Ampere's law is useful only when this integral can be easily evaluated. Okay, means when there is some symmetry aspect in the problem, in the current distribution or field distribution. Okay, Ampere's law gives you the fastest way of finding the magnetic field. Okay, right, now we can see some applications of Ampere's law, right, in the later videos, right. Thank you.